Okay, guys, so we're going to go back to limits. I know we just did the derivative, and we're definitely going to come back to doing the derivative and find some easier ways to get the derivative of a function. But we're going to do our last couple units on limits before we get into that. So we're going to talk about limits at infinity, and it says right here not to be confused with infinite limits. So let's talk about what the difference between those two are. Okay, so an infinite limit is one where when you do your direct substitution, right, you get a constant over zero, which means the graph has a vertical asymptote, which also means that the limit doesn't exist. Sometimes you'll see this written as an answer infinity, but technically infinity is not a numerical answer. So this would also be a case where we would say that the limit does not exist, okay, because the graph is shooting up to infinity as x goes to 2. All right. Limits at infinity are when we're doing the limit as x approaches infinity or negative infinity. Okay, it could be either one of those. That's limits at infinity. So what we want to do is we want to think about what the function is approaching as x gets really, really large. So we can't really do direct substitution because infinity is not a number, but we can think about what happens with the function. So if we plug infinity into x, a really large number, all right, minus 2 and then square it, we're going to get a really large number. And this value is going to get larger and larger and larger. And since it's on the bottom of a fraction, that means that the fraction is going to get closer and closer to 0. All right. And this is basically if there's a horizontal asymptote. So if x approaches infinity, if the function approaches a constant, that means the graph has a horizontal asymptote. And we've seen horizontal asymptotes before with rational functions. So we're going to come up with our rules based off the same rules that we had with rational functions. All right. So when we were doing horizontal asymptotes for rational functions, we wanted to compare the degree of the numerator with the degree of the denominator. Okay, so this is the same as now a limit at infinity, because that's what a horizontal asymptote would be. So let's review the rules. So if the degree of the numerator, the top, is less than the degree of the denominator, then the limit as x goes to infinity or negative infinity. So this should really say plus or minus infinity because it doesn't matter, all right, whether it's positive or negative. But the rational function r of x, which would be n of x over d of x, some type of fraction, would be 0. So if the degree of the top is smaller than the degree of the bottom, the limit would be 0, because that's also before we've said the horizontal asymptote would be y equals 0. If the degree of the numerator is equal to the degree of the denominator, so we have a polynomial over a polynomial where the degrees are equal, the limit as x goes to plus or minus infinity, again, that's what that should say, would be the ratio of the leading coefficients. Okay, so the leading coefficient of the numerator over the leading coefficient of the denominator. And if the degree of the numerator is greater than the degree of the denominator, then there would be no limit, okay, because that would mean that the rational function would be getting larger and larger and larger, so it wouldn't approach a constant, which means the limit doesn't exist. Sometimes you might see infinity put here, but really there is no limit. All right. When we did rational functions, we talked about slant asymptotes, but that's not a horizontal asymptote. Okay, so the idea here, limits at infinity, we're trying to find just the horizontal asymptote. So using these rules, these problems are really quick to solve. So we're going to go through these 6 examples, and we can go through them pretty quickly. All right, there's not a lot of work that has to be done. So since we're doing the limit as x goes to infinity, this is the only time you're allowed to use this rule. Okay, so you have to see limit as x goes to infinity or negative infinity. We've got a rational function. The degree of the top is equal to the degree of the bottom. So we're going to do leading coefficient of the top over leading coefficient of the bottom, and our answer is going to be 2. If you were asked where this graph has a horizontal asymptote, we would say y equals 2. So it's the same math, but it's just how you would state your answer. The next problem, we're doing the limit as x goes to negative infinity. And again, we have a rational function, polynomial over a polynomial. And the degree, you want to look for the highest degree of the top, and the degree of the bottom are actually the same. So we have to take the leading coefficient over leading coefficient, and our answer would just be negative 5/3. For the next one down here, again, limit as x goes to infinity, polynomial over a polynomial, degree of the top and bottom are equal. So leading coefficient over leading coefficient, our limit's going to be 1/3. Let's move over here up to this one. Again, it's a limit at infinity, all right, positive infinity. Degree of the bottom is bigger than degree of the top, which means the limit would be 0. The next one, again, we have a limit at infinity. Degree of the top is bigger than the bottom. that will mean that the limit does not exist. And then for the last one, we have to think about this one a little bit carefully, because this is not technically a polynomial over a polynomial because we've got this square root. But we can still use the same shortcut. Now we have to be a little careful. So we're doing the limit as x goes to negative infinity. So if we look at the highest degree term, which would be this, 2x squared, but it's inside of a square root. So the top would really be behaving as square root of 2x squared. And if you take the square root of x squared, remember that equals the absolute value of x, not just x, but absolute value of x. So the top really has the same behavior as square root of 2 times absolute value of x. And then we have an x on the bottom. So really it's the same degree over the same degree, all right? Because square root of x squared, that would be linear. Over x, that would be linear. So we would do leading coefficient over leading coefficient, but we have to be a little careful. So since the top is always going to be positive, and the bottom, if x goes to negative infinity, will be negative, then the limit actually has to be negative. And we would do leading coefficient over leading coefficient. Leading coefficient at the top is square root of 2, because it's inside the radical. Leading coefficient at the bottom is 1. So our limit here would be negative root 2. If this limit had been limited as x goes to positive infinity, then our answer would have been positive root 2. Graphically, if you want, you can graph this function to see what's happening. What it means is it has two horizontal asymptotes. It has one horizontal asymptote as x goes to positive infinity, and then it has a different horizontal asymptote as x goes to negative infinity. So for these ones, you can use our shortcut, but you have to think about it a little bit more than the other ones, because if x goes to positive or negative infinity, that will make a difference, because square root of x squared is absolute value of x. Okay, so let's look at some examples that aren't polynomials over polynomials, but are still rational. And these are ones we see from calculus a lot. So for this limit, we've got the limit as x goes to positive infinity. So again, it's a limit at infinity, but we can't do the degree over degree because we have an exponential. So it helps to know what the graph of base e functions look like. All right, so this is our graph of y equals e to the x. All right. So if we look at this, if we replaced x with infinity, e to the infinity. So if we look at this graph, as x goes to infinity, e to the infinity also goes to infinity. But that's on the bottom. 2 minus infinity is negative infinity, and the top is a constant. All right. So if your denominator is getting infinitely large, even if it's negative, the fraction is going to approach 0. All right. Doesn't matter what, you're just approaching 0 from the negative side rather than the positive side. So that would be our limit here. So you really have to think about the graph of e to the x to figure out what's happening. But when you do direct substitution, you just want to think about, as x gets larger and larger and larger, what's happening to the value of this fraction. And what we can say is it's getting closer and closer to 0. This next one, we're going to do the limit as x goes to negative infinity of 4 times e to the 2x. So if you replace x with negative infinity, we end up with e to the negative infinity. So again, look at the graph of e to the x. As we go to the left, e to the negative infinity gets closer and closer to 0. And this 4 would just be a coefficient, but the limit of this would be 0 as x goes to negative infinity. Therefore, 4 times 0 would also give us 0. For this third example, we're replacing x with infinity, but we have x on the top and the bottom. So we want to think about what's happening to both functions. So as x goes to positive infinity here, so let's think about the graph of sine of x. So here's our graph of sine of x. So as x goes to infinity, this graph is not going to infinity or 0, but it's just kind of alternating between 1 and negative 1. All right, so it almost acts like a constant, right? Because it's not going to infinity or 0. It's just kind of alternating between two constants. But the bottom is going to infinity. So when you have a constant over infinity, even though, again, this is changing, but it's not infinity over infinity. That would be an indeterminate form. Okay, but this is it, like acting like a constant over infinity, then this is also approaching 0. All right. 0 is not always going to be the answer. It just happened to be the answer for these. So sometimes when you don't have polynomials over polynomials, you have to look at the functions and see what's happening as x gets really large. Sometimes you might have to do some algebra to simplify the functions as well. So for the homework, there's not going to be a lot of work for some of the problems, because if you can just identify right away what the limit is, there might be a little bit of algebra for some if you've got fractions that are being added or subtracted. You can also add or subtract their limits as well. But this assignment's going to be due on Tuesday. Okay, it's a pretty quick worksheet. Like I said, you just have to write down your answers. There's not going to be a lot of work that goes with each problem. Okay, so I will get back to you guys on Tuesday and we will talk about approximating area under a curve. Have a nice long weekend and enjoy the nice weather.